And our next speaker will be Yiping Lu from Stanford Institute of Computational Math and Engineering. So Yiping got his bachelor degree from Peking University, worked with a bunch of great people, and generate a lot of great work related to inverse problem, optimal control, and statistical learning theory. So Yiping, take it over, and you have your 10 minutes.
Okay, thanks for the invitation and introduction. I will talk about our work about optimization of the deep ResNets. We studied this problem from a continuous steps ODE viewpoint. Yeah. So we know that deep learning have an evolution of computer visions. If we adding more and more layers, then we'll have better and better results. So this gives us a question why we need such a deep network. How we study this problem is we just limit the layers of the neural networks to infinity. So let's consider if we turn the layers of the neural networks to the time, then if we have a very deep ResNet, for every small step, I just made a very little difference to the features. Then if we limit the layers to infinity, means that we just turns the time to a continuous time dynamic system. Then what we will get is a first order ODE, and the ResNet can be considered as an Euler discretization of this evolving ODE. But there are also some questionable ways, like the ODE and the neural networks are just like apples and oranges. How the analysis of ODEs helps us to analyze the neural network. We have I think a series of fantastic works have shown that if you have this relationship, you can encoding physics to neural network. As an example, you can have stability, you can approximate the optimal transport map, you can find out the task structure, you can do physics learning. Uh, but today, I want to answer this question in another viewpoint. I want to see how the ODE analysis can help us to understanding the optimization of the neural networks. Yeah, but for the other two parts, like the modeling and inferencing part, you can go to my homepage to find out more information. Yeah. So why we need this OD analysis for understanding the optimization of deep neural networks? We are different from the non-convex optimization approaches, just like we just consider minimize of fx. What we considered is like our objective is exactly a loss function with a neural network in it. So we write down our objective as minimize the loss function plus regularization terms, and we put our neural network evolution into the constraints. The T here is the layer number. So you can see we just put the layer by layer structure in the constraints. And we just replace the continuous, the layer by layer structure to a ODE so that we can just have a very simple continuous form. And you can also write it down, all the things in just the discrete form. They are the same, but for the simplicity, we just do the optimal control problems analysis. Okay, so if you want to solve this optimal control problem, the basic way is to use the gradient-based training. For the gradient of this optimal control problem, if you know something, you will write down the adjoint equation, right? So maybe some people will ask, does the adjoint equation is a new method, new backpropagation method? Actually not. What we can prove is that if you have a neural network, like as an example, if your neural network is discretized by a Euler discretization, and your adjoint equation is also discretized by Euler discretization, is what we done in ResNet. If you do so, what you can prove is that the adjoint equation is exactly the backpropagation. If so, why the ODE's approach can give us more? So I think in the neural ODE paper, what they discovered is invertibility. But in our work, we'll tell you more. We can just utilize the structure of the layer by layer composition. Yeah, so what we want to show today is if you want to consider the problem of to optimize a neural network, you should consider all the optimization neural network loss function. You should consider all of the things together, but not just optimize um, uh, arbitrary non-convex functions. Yes, there are also other frameworks to consider this problem. As an example, you can consider the Hamiltonian Jacobian dynamic programming approach. You can also extend this approach to some SDE. Yeah, for the theory part, if we write down this problem, it's still a non-convex problem. So we still can't prove any theorem for it, even for the convergence of the gradient descent. So what we can do is we want to find out a continuous model with a good landscape. So let's just go back to a quick overview of the convergence proofs of the neural network. The first one is the neural attention kernel, like we linearize the model and just analyze it on the linear models. And another regime is called mean field regime. What it considered is like it doesn't consider the landscape respected to individual weights. I just consider the landscape respected to the distribution of weights. In that case, you will find out it is a convex function in L2 space. And the stochastic gradient descent is the Warshawski gradient flow. For the first neural attention kernel approach, the feature is lazy and it is not data dependent. So we want our model lies in the second regime, like the active learning regime. We should let our data feature to be data dependent. But for the mean field regime, it's very hard to generalize beyond 2 layers to have the same guarantee. So what we considered is we just have our ResNet model, our ODE model of ResNet also comes to respected to distribution of weights. So we just consider our ODE and the weight here, the residual blocks is sampled from a distribution like rho theta t. The theta is the weight space and the t is like the depth. So we just consider the our residual blocks is sampled from a distribution of weights. Let's see what we can prove for the landscape of this model respected to the distribution of weights. Okay, so you can also write down the adjoint equation is all the same. And I think I can just show you the result. The result is here. How we can prove that is we want to bound the difference of the backpropagation process of the 2-layer nets and the ResNet. What we can prove is that if you write down all of the 2 things in distribution way to see what's the difference of the 2 models gradient, what you will find out is that the ResNet will just to have a further computation through adjoint equation. So if you prove some lower bounds of your evolution of your adjoint equation, then what you can prove that your objective local minima is also a global one, but it's still not convex. We can just prove that the local minima is a global one. So what you can have is like if your gradient flow converges, then the convergence point is the global minimizer. Yeah. We also design a numerical scheme to discretize our model. It is a slightly different from the backpropagation algorithm. And for our algorithm, we can show that it's slightly better than SGD. We are not saying that you are using the mean field training can give you better result. We just want to show you that our limiting method for the ResNet to the new model, the model inspired by the new model is doable in stochastic gradient descent. Yeah, so for take-home message is that you should have a nice continuous limit of the deep ResNet where the local minimizer is global one in L2 space. You should use this model, but not the previous ODE, the naive ODE model. But our analysis is not so good. We still doesn't have analysis for the Warshawski gradient flow in global sense. We also doesn't have analysis for our numerical scheme, so we still have a gap to the true training of the deep ResNets. Yeah, and we also want our point of view can give us our insight to design optimization algorithm. Here, the example, I will give a very fast example here is like the adversarial training. The adversarial training is very hard because if you want to generate adversarial example first, then you do the gradient descent. But to do the to optimize the problem to have the adversarial example, you need a gradient ascent for many times, like as an example, R times, and R is always 10 in practice. So you can see if you want to have a one step of gradient descent on the weights, you need 10 times to get the adversarial example. So the computation here is very unbalanced. So we want to fix this problem from our continuous ODE view of point. So what our algorithm gives you is like our algorithm is a neural network specific algorithm. Our algorithm can just accelerate the computation of neural networks. That's the benefit of our ODE model. Okay, so I will introduce the algorithm later because the time constraint. Let me just tells you the main idea of design algorithm. What we do is we write down the first order condition. It is called maximal principle in optimal control. It is very similar to KKT condition, but it's just slightly stronger than KKT condition. So if you write down the or the KKT condition or PMP maximum principle here, what we will find out is you will have 3 formulae. the first one is forward equation. It is the same as your neural network. So you can see the first one is just your constraint. In KKT, you can just it as a constraint. The constraint, you should write it down. And for the second one, it is, you will find out it is the adjoint equation. So in KKT, it's just the condition for the dual parameters. So the adjoint equation is the backpropagation on the feature map. If you calculate the adjoint equation, you can get the gradient of the feature maps. And for the weights, if the weights will satisfy a layer by layer maximal principle. So if you consider this kind of structure of the KKT condition, a natural algorithm you will design, you just do the Jacobian iterations. You do the first one and the second one and the third one. And for the third one, you will find out the adversarial example, it just appears in the first layer. So it means that if you want to get an update of your adversarial example, you only need to focus your computation on the first layer. So this is our idea of design of the algorithm. So our algorithm is just to do the adversarial example attack into two parts. The first part is just a one time of 4 backpropagation, but we have a multiple times attack on the first layer. So we just attack, you use the first layers, and we have this mn loop. So we can have m times n's attack by just m times of 4 backpropagations. In practice, I think we take m as 5 and n as 3. So we have 15 times of attack by just 5 times of backpropagation. This gives us a very fast attack algorithm. So we also tried our method on the benchmarks, and you can see for our method, we have succeeded the previous method by 5 times, because if you have a trace, the m to be 5, it should be 5 times. If it is 3, it should be 3 times. So you can see to have the same performance as the previous method, we can become 5 or 4 times faster. It is because we just have 5 times of 4 backpropagations, but we have 15 times of attack. The 15 is slightly larger than 10 because all attacks power can be slightly different from the previous PGD attack, but we can get the same result by almost 5 times faster. So for the take-home message in this part is like we write down our optimal control problem for the adversarial training. You can find that out. It is a differential game. And for the algorithm, you should split it into 2 parts. For the first part, you do a full backpropagation, and then you focus your attack on the first layer. So the UPO method, because it is propagate once, we call it UPO, you only propagate once. The UPO algorithm can be understood as a discretization way of solving PMP. So I think this is how our work discovers the structure of the neural network via the ODE formulations. So I think here is the ending slide, is like how the ODE's point of view can help you. It's like you have invertibility, you can find out the structure of the neural networks, and also there are some new directions to finding out the ODEs that are easy to solve. So the ODE formulation is not just to encoding physics to the neural network, we can do more. So I think you can just go to my homepage to see further details. Okay, thank you.
Thank you very much, Yiping. I guess myself is enough familiar with this work. So let's see if we don't got more questions from the Zoom chart. Maybe we could take any possible discussion offline just for the schedule purpose. Thank you very much, Yiping. Okay.